This video is a review of function transformations and modeling. That's AP Precalculus topics 1.12 through 1.14. If you appreciate this content, please don't forget to hit that like button. Number 1. Let g be a function that is a transformation of function f such that g of x equals 3 times f at x minus 2. Describe the transformations of the function f that result with the function g. If a, b, c, and d are positive constants, then these are the transformations of the parent function f of x. The transformations that occur on the outside of the function are vertical transformations. For example, a multiplying in the front is a vertical dilation by a factor of a. D added on the end is a vertical translation by D. These vertical transformations work just like they look. If a is bigger than 1, then f will become taller than it was. If a is less than 1, then f will become shorter. If d is positive, then f will move up. If d is negative, f will move down. Changes on the inside of a function are horizontal transformations. These work the opposite of the way they look. For example, if b is greater than 1, then the function gets shorter horizontally. For example, if b is 3, then we have a horizontal dilation by a factor of 1/3. That's why we say horizontal dilation by a factor of 1 over b. If b is less than 1, like 1/3, then the function gets longer horizontally. A horizontal dilation by a factor of 3. The horizontal translations are also the opposite of the way they look. If c is positive, the function will move to the left. If c is negative, the function will move to the right. That's why we say horizontal translation by negative c. A negative sign in the very front is a reflection over the x-axis. In a sense, this is a vertical reflection. So it goes along with the fact that all changes on the outside of a function are vertical transformations. A negative sign on the inside of a function, like right here, is a reflection over the y-axis. This is sort of a horizontal reflection. So it goes along with the fact that all of the horizontal transformations result from changes on the inside of the function. This 3 in the front is a vertical dilation by a factor of 3. The minus 2 on the inside is a horizontal translation by positive 2. Notice that the horizontal transformation is the opposite sign. Number 2, let k be a function that is a transformation of the function h, such that k of x equals h at 4x minus 1. Describe the transformations of the function h that will result with function k. A number multiplying on the inside is a horizontal dilation, but horizontal transformations are the opposite of the way they look. So a number bigger than 1, like 4, will be a horizontal dilation by a factor of 1/4. And the negative 1 on the outside is a vertical translation by negative 1. Number 3, let r be a function that is a transformation of the function p such that r of x equals 5 times p of x over 2 plus 3. Describe the transformations of the function p that result with the function r. A number in the front is a vertical dilation, so this 5 is a vertical dilation by a factor of 5. A number added or subtracted on the end is a vertical translation, so this plus 3 is a vertical translation by 3. I've rewritten r of x to make it easier to see the transformations. A multiplier on the inside of a function is a horizontal dilation. Horizontal transformations happen the opposite of the way they look, so multiplying by 1/2 gives a horizontal dilation by a factor of 2, the reciprocal. Number 4, let n be a function that is a transformation of function m, such that n of x equals negative 2 times m at negative x. Describe the transformations of the function m that will result with the function n. This negative in the very front is its own transformation, a reflection over the x-axis, sort of a vertical reflection. A negative on the inside is a reflection over the y-axis. The 2 in the front is a vertical dilation by a factor of 2. The table below gives values for function f at selected values of x. Use the table to answer 5 through 6. Number 5. Let g of x equal f at 3x plus 2. Find the following values. G at 3 means plug 3 in for x, right here. That makes 3 times 3, which is 9. So now we have f at 9 plus 2. We can find f at 9 on this chart. Here's 9 and here is f at 9. So g at 3 equals negative 6 plus 2, which is negative 4. G at negative 1 means plug in negative 1 for x right here. 3 times negative 1 is negative 3. So we have f at negative 3 plus 2. What is f at negative 3? Well, here's negative 3. Here is f at negative 3. So g at negative 1 is equal to negative 1 plus 2. Therefore, g at negative 1 is equal to 1. Number 6. Let h of x equal negative 2 times f at x plus 3. Find the following values. Part A. H at 3 means, let's plug in 3 for x right here. So h at 3 will equal negative 2 times f at 6, because 3 times 3. And so h at 3 will equal negative 2 times whatever f at 6 is. Well, here's 6. F at 6 is 5. So negative 2 times 5. Therefore, h at 3 is equal to negative 10. Part B. Find h at 0. H at 0 means plug in 0 for x. So h at 0 will equal negative 2 times f at 3, because 0 plus 3 is just 3. Now h at 0 will equal negative 2 times whatever f at 3 is. Well, here's 3. F at 3 is negative 2. Therefore, h at 0 will equal positive 4. Number 7. The function k is constructed by applying 3 transformations to the graph of h in this order: a horizontal dilation by a factor of 1/2, a vertical dilation by a factor of 3, and a vertical translation by negative 5 units. If k of x equals a times h at bx plus c, find the values of a, b, and c. A vertical dilation by a factor of 3 means a multiplier of 3 in the very front. So a is equal to 3. A horizontal dilation is a multiplier on the inside, so it's going to give us the value of b. However, horizontal transformations are always the opposite of the way they look. So a horizontal dilation by a factor of 1/2 will lead to b equals 2, the reciprocal. A vertical translation by negative 5 tells us that c must equal negative 5. Number 8. The graph of y equals f of x consists of 3 line segments as shown on the closed interval from negative 4 to 4. Sketch the graph of g on the same axes above, where g of x equals f at x plus 1 minus 2. The x plus 1 on the inside means a horizontal translation by negative 1. In other words, left 1. This minus 2 on the end means a vertical translation by negative 2, so down 2. To graph the transformed function g of x, all we have to do is take the 4 key points from f of x and move them left 1, down 2. For example, this point, if we go left 1 and down 2, will be right here. Take this point, left 1, down 2. Grab this point, left 1, down 2. Grab this point, left 1, down 2. Then connect the dots, and that's it. Always label your graph. Same instructions for number 9, but the transformed graph h of x equals 2 times f at the opposite of x. The 2 in the front means a vertical dilation by a factor of 2, and the negative on the inside is a reflection over the y-axis. Whenever dilations or reflections are involved, I like to graph the transformation using a table of values. I start by listing off the key points of the original function. For example, negative 3, 3, negative 1, 3, 1, negative 2, and 4, 1. Then I ask myself what transformations will affect the x values. In this case, the reflection over the y-axis, this negative sign in front of the x. So I can get new x values by simply doing the opposite of my original x values. That will be 3, 1, negative 1, and negative 4. Then I ask myself what transformations will affect the y values. In this case, the vertical dilation by a factor of 2. So I can get new y values by multiplying the old y values by 2. So that will be 6, another 6, negative 4, and 2. Finally, I graph these purple points, which give me the transformation. To check your answer, look for the expected transformations. For example, a vertical dilation by a factor of 2 would cause the new graph to be twice as tall. And we can see that is the case. The reflection over the y-axis means the new function should be backwards, which it is. Don't forget to label the graph. Number 10 has the same directions, but the transformed function is k of x, shown here. K of x has 3 transformations that will affect the y values. The negative in the front is a reflection over the x-axis. The 2 in the front is a vertical dilation by a factor of 2. And the plus 1 on the end is a vertical translation by 1. So, based on these 3 transformations, I can get new y values by doing negative 2 times the original y value plus 1. For example, negative 2 times 3 is negative 6, plus 1 is negative 5. Negative 2 times negative 2 is 4, plus 1 is positive 5. Negative 2 times 1 is negative 2, plus 1 is negative 1. There is one transformation that will affect the x values, and it's this plus 3. Horizontal transformations are the opposite of the way they look, so this will be a horizontal translation by negative 3. In other words, I can get new x values by doing the original x value minus 3. So this negative 3 will become negative 6, negative 1 will become negative 4, 1 will become negative 2, and 4 will become 1. Now we just need to plot these green points and connect the dots. Don't forget to label your graph. Number 11. The domain of function h is the closed interval from negative 5 to 10, and the range is the closed interval from negative 4 to 2. Find the domain and range of g, where g of x is h at x minus 5 plus 7. I like to find the new domain and range using small charts. The domain is the set of x values, so the endpoints of the x values are the negative 5 and the 10. The transformation that affects the x values is this minus 5, which is a horizontal translation by positive 5. So I can find new x values by doing x plus 5. So that's going to turn this negative 5 into a 0, and this 10 into a 15. So my new domain is the closed interval from 0 to 15. The range is the set of y values, which went from negative 4 to 2. The transformation that affects the y values is the plus 7, a vertical translation by 7. So I can find new y values by doing y plus 7. So that will turn negative 4 into a 3, and 2 into 9. So the new range will be the closed interval from 3 to 9. Or if you prefer inequalities, the domain and range can be written like this. On number 12, the original domain goes from -4 to 8. The transformation that affects the x values is on the inside of these parentheses. X over 3 is the same as 1/3 x. Horizontal transformations work the opposite of the way they look, so this is really a horizontal dilation by a factor of 3. Think reciprocal. So I can find new x values by doing 3x. 3 times -4 is -12, 3 times 8 is 24. So my new domain is the closed interval from -12 to 24. The original range goes from -7 to 3. The two transformations that affect the y values are the 2 multiplying in the front and the 1 adding on the end. So I can get new y values by doing 2y plus 1. 2 times -7 is -14, plus 1 is -13. 2 times 3 is 6, plus 1 is 7. So my new range is from -13 to 7. The original domain for number 13 goes from -10 to 0. The transformation that affects the x values is the 2 on the inside. This is a horizontal dilation by a factor of 1/2. It's the opposite of the way it appears. So I can find new x values by doing 1/2 times the original x values. So that will give me -5 and 0. The new domain is from -5 to 0. The original range goes from -8 to 6. The transformation that affects the y values is this -3, reflection over the x-axis and vertical dilation by a factor of 3. I can get new y values by multiplying the original y values by -3. So this will make +24 and -18. So my new range is the closed interval from -18 to 24. Always write your interval in order from least to greatest. Number 14 is calculator active. The table above provides data for 7 ordered pairs x and y. Part A. Which function type best models the data in the table, linear, quadratic, or cubic? Explain your answer using the characteristics from the data in the table. Notice that the y values begin and end near 40, but in the middle they fall to a low of 2.1. So, since the y values decrease and then increase, and they are roughly symmetric, a quadratic model would be best. Here's a model answer for linear. Since the rate of change is roughly constant, a linear model would be best. Part B. Write the equation of the regression model for the data in the table. To enter the data into your calculator, hit the Stat button and hit Enter for edit. If there's anything in here, go to the labels at the top and hit Clear, Enter. Now enter your input values as L1 and your output values as L2. To choose a regression model, hit the Stat button and arrow over to the Calc menu and choose which one you want. We decided to go with quadratic regression, which is option 5, so you can either scroll down or just hit the number 5. Before you hit enter, I suggest you always go down to Store Regression Equation as y1 in your y equals area. You can do this by hitting the vars button, switch over to yvars, hit enter for function, and enter again for y1. Now when you hit calculate, this regression equation will show up on y1. Record your regression equation by plugging in the values of a, b, and c. Use 3 decimal place accuracy. Part C. What is the residual for the point whose x-coordinate is 6.1? Remember, the residual value equals the actual value minus the predicted value. So the actual value is what we will find on the table. The value of 6.1 is 3.7. So the residual will be 3.7 minus whatever the predicted value is at 6.1. We can find this using the calculator. Because we opted to have the calculator store the regression equation as y1, we basically need to subtract the value of y1 at 6.1. Since we opted to have the calculator store the regression model in y1, the predicted value will just be y1 at 6.1. To get y1 on your calculator, hit the vars button and switch over to yvars, hit enter for function, and enter again for y1. To evaluate y1 at 6.1, just put 6.1 in parentheses. So this is the predicted value. Since we opted to have the calculator store the regression model as y1, we can find the predicted value by doing y1 at 6.1. And we can just type this into the calculator. 3.7 minus, to get y1, hit the vars button, arrow over to the yvars menu, hit enter for function, and enter again for y1. And then just put the 6.1 in parentheses to evaluate y1 at 6.1. So this is the residual value. In your work, don't put y1 since we called it just plain y. It should be just plain y right here, y at 6.1. Hey guys, don't forget to like and subscribe, but also if you found this video helpful, there's a lot more where that came from. You can click the upper link, which will take you to the whole unit playlist, or you can click the lower link, which will take you to the next video in the playlist. See you there.